Hey everyone, welcome back, and today let's solve Leetcode problem 3370 titled Smallest Number with All Set Bits. So very simply, we're given a positive number n as our input, and we need to return the smallest number x greater than or equal to n such that the binary representation of that value x that we choose contains only set bits. And again, it defines a set bit basically just to be a bit in the binary representation of a number that has a value of 1. So in example 1, we have n to be 5, and the smallest number that's greater than 5 and has all set bits, in other words, our x value for this case would be 7. 7 is the smallest value that's greater than 5 that has all set bits, right? Because the representation in terms of binary for 7 is 1, 1, 1. Guess what? 1, 1, 1, that's all set bits. As we know, the definition of a set bit is a bit in the binary representation of a number that has a value of 1. All of them has to be 1. In this case, it is. Let's go to this next one here. N is equal to 10. The smallest value that's greater than 10 that has all ones in the binary representation, meaning all set bits, or in other words, our x value for this case would be 15. And the reason why is because the binary representation of 15 is 1, 1, 1, 1. Instead of 3 ones like the previous case, it's just 4. But notice how it's still all ones. That's the main kind of takeaway to look at from these examples. And for 3, we can actually use the number itself 3 as long as it also has a set bit binary representation, right? So for the constraints here, we see that our input n integer is going to be between 1 and 1000, which leads us to the main observations that we really need to make. And that is essentially numbers whose binary form is only ones are exactly 2 to the k minus 1. Notice how we see that for both 5, or rather for both 7, 15, and 3. 2 to the k minus 1 are basically all of the numbers whose binary form is only ones, meaning only set bits, right? Notice how 7 is 2 to the k minus 1, where k is 3. 2 to the 3 minus 1 is 8 minus 1, or 7. 2 to the 4 minus 1 is 16 minus 1, which is 15. And 2 to the 2 minus 1 is 4 minus 1, which is 3. All of these values, and in fact any value that has set bits according to this problem's definition, has to be 2 to the k minus 1, where k is some value. So really, in other words, the way to solve this problem is really just determining the 2 to the k minus 1 that's smallest but at least greater than or equal to n, right? That's all we have to try to find out. And once we have that k, we simply return 2 to the k minus 1, as long as it's greater than or equal to n, and it has set bits, right? Because again, a number is defined to have set bits if it is equal to 2 to the k minus 1. And so it's very simple. We don't even need to do much like bit shifting or anything, although we do have to do bit shifting, of course. It's not that complex. It's a very straightforward kind of bit manipulation friendly problem, right? Which brings us to the main kind of solution and the actual coding part. And one last observation to make: if n is already in the form of 2 to the k minus 1, well then that's perfect. That's basically just our input. We can just stop the loop immediately and immediately return n, right? And so that's a good example of that would be example 3, where our input n that we start off with automatically is 2 to the k minus 1, or in this case k is 2, and since 3 is greater than or equal to 3, we simply return n, or in that case 3. Right, so let's go ahead and get into the code here. So we're first going to start with 1, right? And that equals 2 to the 0 power, where 0 is the smallest k for this problem, right? Because we're only dealing with integers. And so I'm going to get power of 2, and I'm just going to start it off to be 1. Right? Effectively, we're just creating this variable power of 2. We're setting it to 1 as our starting value, and it's simply going to represent 2 to the k for some kind of arbitrary k value as we compute through our solution. Now, initially, of course, k has to be 0, because 2 to the 0 is 1, right? And of course, we're going to repeatedly double this to find our required power once we actually get the smallest power that's greater than n, and that's what we eventually return. Right, we eventually return the value of 2 to the k minus 1. And we're going to keep doubling until the power of 2 minus 1 value is at least n, meaning it's at least valid to be able to be returned. Right, and the way we're going to do that is effectively just use a while loop here. So while the power of 2, and of course using the definition minus 1 is less than n, we have to keep going. Effectively, we're going to keep running as long as it's less than n. And in this loop body, we're effectively just going to double our power of 2 variable or value. And once power of 2 minus 1 becomes greater than or equal to n, well then we can simply stop out or get out of the loop. And the loop basically just checks if power of 2 minus 1 is less than n. That's basically just kind of exactly the encoding of our stopping condition here. right? And effectively, again, here we're basically just stating that our loop invariant that we're going to use is going to be 2 to the k minus 1, and that has to be greater than or equal to n. And so we basically have to just keep checking while 2 power of 2 minus 1 is less than n, and against those two values, and simply just double, again, keep doubling power of 2 until we actually kind of break this inequality and it's no longer less than n, right? Meaning it's greater than or equal to n. But while this is the case here, inside of this loop here, we're effectively just going to keep doubling the power of 2 like we talked about. And we're actually going to be using something called bitwise shifting here. And the way we're going to do that is simply just power of 2 and apply that scale factor of 2 by using something called bit shifting, and just do that by 1. Effectively, we're simply just using this bitwise left shifting and appending or changing that by 1, or rather by that factor, to the power of 2 variable. This is really like the main body of our loop, right? Power of 2 bit shifted by 1 is effectively just using an in-placer inbuilt Python bitwise left shift that basically just multiplies power of 2 by 2. You can also do power of 2 equals power of 2 times 2. It's essentially the same thing, but we're using the shift because it's idiomatic and it also emphasizes the whole point of this problem, right? The whole point of this problem is quite literally to actually bit shift. It's quite literally to work with bit and binary representations. And so for this problem, I'm going to be using bitwise to multiply power of 2 by 2. Another way I could have done this is simply just do power of 2 times equals 2. But that isn't, I mean, that's still pretty elegant. It's just that isn't really representative of the problem that we're working with. I wanted to keep it in terms of actual bitwise operations because that's the whole point of this problem. Otherwise, this would be even easier of a problem, right? And of course, we're using this and we're using the shift because really, again, it's important to actually multiply power of 2 by 2 until we actually get 2 to the k minus 1 to be greater than or equal to n. And each iteration would increase k by 1. And so the power of 2 would go from 1 to 2 to 4 to 8, essentially just representing 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and we just subtract 1 each time from that value while it's still less than n, meaning while it's still invalid. And after the loop ends, power of 2 would be equal to 2 to the k, where 2 to the k minus 1 would be greater than or equal to n. And so once this loop ends, we're basically just having that valid kind of answer. We're no longer less than n, and we can simply just return power of 2 minus 1 as our final value, right? As our kind of final loop here, basically, right? Because after the loop finishes, we know that the power of 2 variable has to equal 2 to the k for the smallest k. That still satisfies the condition of 2 to the k minus 1 being greater than or equal to n, right? That's basically the smallest number with all binary ones, with all binary all ones that is greater than or equal to n. Right, and the subtraction would simply just give us the actual number with k ones in the binary representation. So if power of 2 is 8, we'd return 7. If power of 2 is 4, we'd return 15, and so on and so forth, whose binary representations are 1, 1, 1, and 1, 1, 1, 1, 1, respectively. Right, so now I can go ahead and submit this, and as you can see, it would actually be accepted, and it is the most efficient solution possible, right? So kind of as a whole, how are we really solving this problem? Effectively, we're just starting from 2 to the 0, which is essentially just 1, kind of like our starting initial value. And basically, we're just in this while loop checking while our 2 to the k minus 1 is still less than n, we're going to keep doubling our power of 2 repeatedly. We'll just keep checking at each iteration if 2 to the k minus 1 is large enough to be valid according to these problem statements of being at least n, right? And once we actually find the smallest k such that that condition holds true of 2 to the k minus 1 being greater than or equal to n, we then return that actual value of 2 to the k minus 1 being our answer as kind of our x value, right? And again, tying back to that main observation that we made at the start of the problem, only numbers that have the form 2 to the k minus 1 are actual valid candidates, which make this solution rather straightforward and rather elegant and efficient as well, because we're only checking these numbers of in the form of 2 to the k minus 1. right? And so that brings us to the final part of this solution, which is the runtime and memory complexity. So the overall runtime complexity here is actually very, very efficient. It's just big O of log n. And the reason why is because each loop iteration would actually double the power of 2 variable, and starting from 1, after t iterations, power of 2 would be equal to 2 to the t, and then we know we stop once 2 to the t minus 1 is greater than or equal to n. And so if t is greater than or equal to log, t is basically greater than or equal to log 2 of n plus 1. And so the number of iterations would be proportional to the number of bits in n, which would be big O of log n. And we know each iteration just does some big O of 1 work, but that doesn't really affect our runtime complexity, and so our overall runtime complexity is big O of log n. And our memory or space complexity is actually constant or big O of 1 because we're not actually using any extra data structures or any auxiliary memory. We're only using this extra integer variable power of 2, which is not going to scale linearly with our input, right? It's simply constant regardless of how large our input size is. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.